lights. See if I can drive this. Oh, okay. How's that, guys? All good? Sound check, picture? Okay. Hi, guys. Good evening. I think this is actually our first welcome to, introduction to astronomy for after lockdown season 2. So, just the way it's worked out. So, welcome. Hi, guys. Come on in. Yes, Gavin. Come on in. Yeah.
The Northern Star Party. We've got to get this right. Yeah. At the moment, we set 60 limits because of coronavirus. We're slightly over that, but if people really want to go, we can put them on a wait list. But 61 people have paid up already, and there's three others that have paid for the earlier one that say they're likely to come. So, but there may be a few people pull out. So just email me if you want to go, and I can put you on a wait list. But at this stage, we don't want to go over the 60 because of safety things and what the school want and so on, and the people who run the camp. Any questions about Wakarau? Who's going here, by the way? Oh, quite a few, yeah. Well, if anyone's still interested, just email me and I'll put you on a waiting list.
What's your email address, Gavin? GavinLGN@gmail.com. It's on the notice anyhow. The notice is still in the journal and on the website. So, GavinLGN@gmail.com.
I just one thing about the journal. We had a bit of a mishap over the weekend because the journal was meant to come out over the weekend, but Chris's email was actually went over the limit of the amount we can send out of mail for about 3 months.
Sorry.
So that's why the journal came out a little bit late. But, I think it's because you sent the extra.
I did, yeah. I'm the culprit. Sorry.
So anyway,
But I had fun doing it. That's the consolation. Right, we all good to read rock and roll? Yes, Niven.
Speaking of emails, if you're waiting for your birthday dinner tickets, I've had an email from them as well, and that it takes a lot of work to do it, but I'm sending out the tickets either after this or tomorrow. So if you bought a ticket and you don't get an email, contact me on my phone number's in the journal, which you should have got. Or just at events at astronomy.org.
Right, we ready to rock and roll, guys? Buckle up, we're going to have some fun. Okay. So, gravity is what we're talking about tonight. Gravity is everywhere, whether it's your friend or your foe. Some of it's our friend, sometimes it's our foe. It is everywhere. Guess where this is? This is a truck parked at the end of my street sometimes on the weekends. So I called the driver up and said, hey, what's the story behind that? And he discovered what gravity was about one time when he forgot to put the brakes on and jumped out of his truck. So heading down the hill, and he suddenly realised, oops, so he renamed the truck Gravity. I thought that was just a quirky little start. Okay, so gravity. What is gravity? A bit of a brief definition, I suppose, would be it's a natural phenomenon that we experience of an attractive force between two bodies of mass. I suppose trying to put some words together, you ask them what's gravity, and most people would come up with something like that. So what does it do? Because we all take it for granted. Who thinks about gravity every minute of the day? I certainly don't. Not unless I've dropped something on my toe. Yeah. So, it holds us down to the Earth, stops us from floating away, keeps the moon in orbit around the Earth and the other planets around the sun and so on. Well, we don't think too much about it. But what exactly is gravity? What's going on there? Is there more to the picture? So that reason tonight's talk is titled Gravity, Past and New Ideas of what gravity could be. So to do this, broken it into 3 sections. First, insights and descriptions of gravity, in particular their successes and problems. So that'll be myself, their ideas and descriptions, Galileo, Newton and Einstein. And then my friend and medical colleague John Wishart is going to talk on quantum gravity. It's sort of the new area of exploring about gravity. Then we're going to sum it all up, wrap it up, and of course no one leaves the room without getting homework in any of these talks. There's always homework, and it will be marked. So, Chapter 1, Insight and Descriptions of Gravity, their success and problems, by three guys, Galileo, Newton and Einstein. And I chose these three. What makes these three guys so clever? They had the ability to make observations, whether it be in a real life experiment that they set up, or whether in the context of Einstein, he had these thought experiments going on. But they were able to do experiments and make observations, which a lot of us can do. But these guys then looked at the results and how the experiment progressed. They had an uncanny ability to recognise that nature throughout the experiment was giving them little hints of maybe what's going on, that 99% of us would just go over our heads, would just be lost on us. We wouldn't see that little hint from nature. And that little hint that these guys were able to pick up on with their experiments, then they were able to get these insights to create ideas and principles, and that was another step. So that's really, any great scientist, that's what pulls them apart from the rest of the pack. So first of all, Galileo. A lot of people consider him the father of science, the first guy who started come up with hypotheses, do experiments and so on. Another little side note is about a year or so ago we were talking about Galileo here, and someone stuck up their hand. Why do we call him Galileo when his name is Galileo Galilei? Why don't we call him Mr. Galilei? And so I looked that up, and of course Galileo in his time, this was at the time of the European Renaissance, when a lot of the artists were very active. And it was just trendy in the day for artists to call themselves, promote themselves by their Christian name. And Galileo was in that era, and he thought, I'm going to do that. I'm an artist, sort of. So that's the story behind, we just call him Galileo. So he introduced what we know as the Equivalence Principle. That he, by demonstrating that gravitational acceleration for all objects is exactly the same. For example, I get a tennis ball and just a little bit of piece of plastic I found lying around the garage that the cat had sat on. If I drop these, you sort of tell you, oh, this one's got to reach the ground first. But yeah, you guys can tell me which one's going to hit the ground first. Both together, aren't they? Yep, both together. So he was able to demonstrate that. So let's look a little bit closer and see how he did that. That's really important, that equivalence principle. That was a key thing that he first recognised. And of course, he lived down the road and climbed up the leaning Tower of Pisa, and he dropped ball bearings off, so the same shape but of different masses and sizes, and dropped them off the top of the tower. And he found that counterintuitively, they both, or all the different balls, hit the ground at the same time. So that told him that this rate of fall due to gravity of an object is the same independent of its mass. So that was one little thing. And then he's got other people to stand up and do it, and he tried looking from below, and he realised that, yeah, they're hitting the ground at the same time, but it all happens so quickly you can't really tell, is this acceleration, is there an ongoing acceleration, or do they just reach a certain speed and it all, and the velocity remains the same, or are they continuing to get faster and faster? And it was really too difficult to tell from that. So he came up with a very brilliant experiment. He got a series of ramps of various degrees of incline and of various lengths, and got ball bearings of various sizes and weights and masses and so on, running them down. And here's the clever bit, at little points along the way, he set up little clickers and bells. So as a ball went past, and flick, bing, and the bell went off. And he had a whole line of clocks that would measure when each bell went off. So he could then determine the rate at which the balls were coming down and whether they were speeding up or not. And it was through that experiment he showed that indeed, yes, gravity is a force of acceleration. Or probably better put, gravity causes masses to not only start moving, but to accelerate. Their speed goes up and up and up. And the other thing as part of the equivalence principle, he showed that it was the same for all balls. The acceleration rate, which is 9.8 metres per square second, is exactly the same no matter what the weight of the ball. So that's what Galileo showed, and they call it the equivalence principle. That was a big step forward. So this was the improvement, because the old sort of saying with the hammer and the feather, and of course you try and do that on Earth, you know what's going to happen, air resistance, the feather takes its time to reach the ground. So one of the Apollo astronauts thought he'd try that same experiment, but on the surface of the moon, where he had his hammer, and the feather, held them up, dropped them, and watched them go down. There's no air resistance, so the feather could just fall straight down. And sure enough, they both hit the ground at the same time. So just a little quirky thing. Can anyone name who this astronaut? Now, not Chris, because Chris is the master of Apollo astronauts. I'm going to give him a piece of chocolate right now, Chris. So that shuts you up for starters. So can anyone tell me who? Sorry, no. Alan Shepard. No, he was the commander of Apollo 14. Marilyn.
Dave, is it Martin? No. I've got his
Scott.
last name.
Yeah, correct. Yeah,
Dave somebody.
Yeah, Dave Scott, correct.
Oh.
Well done. You know your clearly you know your astronauts.
No, I know Neil Armstrong.
Yeah. Alan Shepard was the first American in space. He was the commander of Apollo 14. So this is Apollo 15. Yeah. And how you know that also is he's got the red stripes, because Apollo 11, 12 and 14, they had nice pictures of them all running around. They realised afterwards who's who in some of these pictures, so they introduced the red stripes on the commander. Okay, so that was Galileo's contribution. So how about Newton? Newton was a clever guy, and incidentally, he was born 1642, the same year that Galileo died. Quirky. Yet again, further evidence. Okay. So he gave us three important insights, and he was sitting in the garden. No, an apple did not fall on his head, but he was sitting in the garden and he just saw an apple fall to the ground. And incidentally, this tree is believed to be a sort of some genetic link to the original tree. It's sort of a great-grandparent. What is it?
Hold weight.
Sorry, does he?
Is it argument hold weight?
Sorry.
The argument.
Yeah. Okay. So he gave, just watching this apple fall to the ground, gave him three important insights. And once again, these guys, their minds ticking over at another level. You and I would just see an apple fall down. Oh, that looks nice. I'm hungry. But he just thought about that apple falling. And he made a simple observation. The apple falls straight down. It doesn't shoot off in another direction. It falls straight down, which would be towards the centre of the Earth. So that was a little insight that we take for granted. And he also suddenly realised, it dawned upon him, he'd been studying and thinking about the moon going around the Earth and so on, the Earth around the sun, about the movements, and it suddenly dawned upon him that same force of gravity, which they call gravity, of the apple falling down, was exactly the same force. They weren't different. Because up till then they thought, well, maybe the local things that we experience here is different to all the heavenly movement of the heavenly bodies. And he suddenly had the insight, it's actually the same attractive force. The moon would just head off in a straight line, but the Earth keeps pulling it around and keeping it in a nice circular orbit. So it was universal, was the key there that he realised. He also realised that this attractive force is a function of both the masses, the apple and the Earth, not one of the two, or not just the moon and the Earth, and also as a function of the distance between them. So he realised that, and then he was further did some more calculations, and he was able to quantize, actually create a proper formula, which is Newton's universal, meaning yes, it accounts for all things that we observe locally, and also the planetary motion, the universal law of gravitational force. And he decided, well, he clearly deducted that the force is a complement of goes between the two surfaces. Here's the moon and the Earth. And how you calculate that degree of force is the gravitational constant, and really a constant in science, really, it's just something to marry together real nature and just the units that we happen to, that us humans happen to use. You always get a constant. So they worked out what the gravitational constant was, And it's a function of multiplying the mass of, say, the Earth, times the second mass, say the Moon in the circumstances, divided by the distance, r, between them, squared. So that, and interesting enough, how he came to that, he actually worked out the period of the Moon, worked out he knew the mass of the Moon and so on, and worked it all out until he found that the formula that worked. So the implications of that is that, say you had sort of a certain force between these two bodies, if you doubled the mass of one of those bodies, the force between those two bodies would double. If you doubled the mass of two of them, the force would increase by a factor of 4. Similarly, you divided by the distance between the two of them squared. So if you doubled the difference between them, the force is going to be only a quarter as powerful between them. If you halve the distance, the force between the two of them are going to be 4 times. So that was a great insight, just that apple falling down, but of course he'd been thinking about things earlier, suddenly realised this is a universal thing that's going on and you can quantitize it. So, Newton's universal law of gravity does work for most of the stuff we're familiar with in our local environment, most of the solar system, day to day. They went to the moon. All the calculations of NASA going to the moon trajectories is all based on Newton's formulas. So it all worked, but there was a problem. Now, Brett, another astronaut question. Who can tell me, this is astronaut here jumping for joy, who can tell me who this astronaut might have been?
Apparently John Young.
Really? Oh, Han, you're the one. There you go.
Oh my gosh.
You know, I'll tell you why Hannah knew that. She knew that because she knew, first of all, it was a commander, he had the red stripes on, and she also very cunningly, so cunning, tell you what, I'll call it a weasel, she saw this instrument in the background, and that's a ultraviolet spectrometer they used to study the sun. And that was Apollo 16 took that instrument up. So that's the giveaway that this is Apollo 16, and the other giveaway is the stripes, that's the commander, so well done.
And they've got an electric car.
And they've got a Tesla electric car there, yeah. Eat your heart out, Elon Musk. So there was a problem with it. It doesn't account for all things. In particular, the one key problem that they picked up early on is the orbit of Mercury around the Sun. When a planet goes around the Sun like Yay, now you can see the plane of its orbit. And they noticed that the plane of Mercury's orbit just kept rotating and moving around. Furthermore, the point called perihelion refers to the point in an elliptical orbit where the planet is closest to the Sun. That's called the perihelion. So not only was the orientation of the plane of the orbit just quietly shifting, it's called a precession, the point of perihelion in the orbit was also shifting along as well. So Newtonian physics just could not explain that. That was an unknown. And that was the clue. As good as this whole thing was for everyday life and most of the observations they made in the solar system, it was incomplete. There are other things going on. And interesting enough, the whole idea, it never sat right with a lot of scientists, including Newton himself. He even fessed up. I am uncomfortable, he said, with the idea that there's some strange, mysterious, invisible force that acts instantaneously over distances between two objects. A lot of scientists said, yeah, we know the equation's working for most of the time, old Isaac, but just unhappy with this, and he admitted himself. It just didn't quite sit comfortably with everyone. So there was a couple of clues that things weren't quite right. And along came this fellow, Einstein. And you recall Einstein in 1905 had a couple of very important, he did a lot of important work, but two key ones. In 1905, he announced his work on the special theory of relativity. And a lot of things came out of that. In particular, one of the key points in the special theory of relativity was that you can't yeah, Warwick, did you want a question?
Is it correct?
Sorry?
Anyway, he said it in 1905.
Yeah.
They didn't work. All the time. This.
1887.
It's mine.
Yeah, sorry. No problem. I'm really great. I put that there just for you, all right? Thank you so much. I'll give you another chocolate, but I ain't got none. I ate the last one on the way down. Sorry about that. But no, okay, so one of the points in his special theory was that time and space are entangled. You cannot disentangle space and time. They're part of the same entity. They're very much closely related to one another and entangled with another. That you cannot, under any circumstances, disentangle. And then, of course, he came out 10 years later with the General Theory of Relativity, which involved explanations of gravity. So there's 4 things I want to touch on with Einstein's work. One is Einstein's Equivalence Principle in comparison to Galileo's. We'll talk a little bit about Einstein's field equation, what it means, and in particular what things it predicts about the universe. Then we'll talk about the successful observations that have been made that help validate General Theory of Relativity. And then, yep, there's a problem with this one too. It's still incomplete. Picture of gravity. So, Einstein was famous for his thought experiments. In particular, he did a couple of thought experiments related with this, which he called his happy thoughts. Because it gave him very happy insights into really what was going on. And he suddenly realised with the thought experience, let's say get a physicist, let's lock him up in a box, a sealed box, with no windows, so he's got no idea where he is. We hoist him up, big cable, nice big height, and then we cut the cable. Why? Because he's a physicist, no. So we cut the cable and let him drop. He doesn't know that. But what he experiences is he's in a state of free fall. And what he experiences himself as a person and around him, and should he do any short experiments involving other items of various masses in there as well, is no different if you got that same physicist with those same experimental objects, put them in that same sealed box with no windows, and just put it somewhere in outer space, well clear of any major objects. And both circumstances, the physicist and his experiments that he's dealing with, all different masses, say ball bearings of different sizes, they're all in a state of free fall. And if you asked him, he could not tell you which circumstances he was under. All objects, the other thing there is, as I've alluded to, all objects of different masses also will behave in the same way, so his experiments won't be any different either. You might think, well, that makes sense, but yeah, that was very clever. The other part of it was, with his thought experiments, similarly, he said if you put this physicist in the sealed box with no window, just sat it on the surface of the Earth, under the gravitational acceleration, should we call it, G, which is 9.8 meters per square second, with his experimental ball bearings or whatever he's got up there. Also, you put him in a box in a rocket and start accelerating the rocket at that exactly same acceleration rate. Similarly, he could not tell you which circumstances he's under. He would experience the same sensation or perception, if you will, and his experiments with different masses would behave exactly the same. So they call that was Einstein's equivalence principle. So, his insights, there were 2 main insights he got from there. One is there is no attractive Newtonian force. Sorry, Isaac, there is no force going on between objects. It's just a perception of a force. And the perceived force involves the properties of space-time and the effects that mass have on space-time, as we're about to talk about further. The second insight was pretty much what we are going to talk about. What mass does to space-time, it warps it, deforms it, distorts it. And that, Einstein not only came up with these 2 brilliant insights that even he thought at the time were crazy, but that's what he came up with. He was able to quantify that with his field equations. Just like Newton's law, the force equals G times mass 1 times mass 2 divided by r squared, Newton says, I can do the same, I can quantize this. So that's where Einstein's field equations come At first glance, you might think, whoa, that looks all a bit complicated, or maybe you might be thinking that looks a bit simple, or whatever. But you break it down, and actually it's not too difficult as it's written here. But the tricky bit is, when you start lifting the hood off it, you might think, well, I thought this took them 10 years to work out. It is very clever, and it's elegant and simple, but underlying it, both the subscripts here, all these represent vectors, 4x4 matrices, vectors, for time and for 3 dimensions of space. You start expanding this out, and it expands into 10 different equations, very complex differential and linear equations that even Einstein had to employ mathematicians to help him out with it. So, but isn't that great? That's, I suppose, the brilliance of the man. You can get some really complicated multifactorial stuff, bring it down to make it a nice simple equation that then, if you wish, you can expand on. So let's not get too caught up, get phased by this. It's pretty straightforward. On the right-hand side of the equation, well, first of all, I'm jumping the gun a little bit. This, I wanted to make a point here. This equation is analogous, which I'm going to show you, to Newton's Universal Law of Attraction, which was the one we said. You might think, really? You're kidding me. Let's see how. So, let's look at the right-hand side of the equation. 8, you know, pi, you know, the gravitational constant, g, c is the speed of light, power of 4. Here's your little your script representing 1 for time and 3 for spatial dimensions. The t stands for tensor, and a tensor is a 4x4 matrix. It gets very, very complicated, but the 4x4 matrix or tensor represents figures or quantization of the amount of mass, energy, momentum, and pressure in small little tiny regions of space. And remember, of special relativity, I should say, one of the other things that he stipulated was mass and energy are all in one. So mass, energy, momentum, in other words, how it's moving, the pressure it's creating. They put all that into a 4x4 matrix. They create these tensors, and that's what the T stands for. I won't go any deeper than that because I'm not capable of it myself. But you get the gist. The right-hand side of the equation represents how matter sums up the matter, what it's doing to space-time. And that sort of tells you how space-time curves. Because on the left side of the equation, these figures here represent how space in a very small, tiny region is actually curving or being distorted or altered. And here it is here. So what's the matter tells space-time how to curve. And the point of this, the equation then goes back onto itself as an equal sign, they're both equivalent. The curvature of space-time then tells matter how to move or how to behave. So that sort of a circle goes round. Matter tells space-time how it's going to warp it and distort it, and then the warping and distorting of space-time tells matter how it's going to behave in that geometry. There's a very famous quote from a physicist called John Wheeler. He said, space-time tells matter how to move, and matter tells space-time how to curve. That was the original quote. I actually prefer it the other way around. Matter tells space-time how to curve, and then that curved space-time tells matter how to move. But the point being is that so interrelated, and that's what that equation is really alluding to, and showing you. So in summary, gravity is not a force, it's a perception of a force due to the curvature of space-time. So you put a big hunk of mass in some space-time, it warps and distorts the fabric of space-time, and that distortion and curving of space-time, when we're in that distortion, we perceive that as a force pulling us down, gravity. But there's no force there. So how does the curvature, what does it look like? And the easiest way, it would be so hard to imagine this on a 3-4 dimensional basis. So we typically use the convenience of just sort of 2D into a 3D dimension thing here, representing a thin rubber sheet, and you put a ball on it, and you see it. And that, most people can relate to that, how the deformity occurs. So Einstein equation, in summary, describes how the distribution of mass, energy, momentum, and pressure throughout the universe distorts and shapes the geometry of space-time over these little small regions, and it all adds up. And yep, those equations will tell you exactly how, if you've got a certain mass, a certain density, and plonk it in space-time, the equations, if you work through them, very complicated, but a computer would do it, it would tell you exactly how space-time, to the degree at which it's deformed. And that in turn The curvature affects the motion of masses. And you can see here, these little red balls going around, these are like little planets or orbits, if you will. You can see them rotating around, and you also see little flashes of light, and see light's being bent as well. And the reason behind that, suddenly with these disturbed and distorted, warped, curved space-time, mass and light travels the shortest distance between two pathways. And the technical term is geodesic. The word geodesic just means the shortest point between two objects in space. And for linear space, it's easy, it's just from here to here. But you start getting curvatures in space, or say on a planet or something like that, you can see these geodesic lines suddenly start heading off at different angles. And they start getting curved, and that's what's going on here. There's light's being bent, and suddenly you're getting these objects here that are going around, because the shortest points are from here, like that, around something. So that's why you get objects in orbit around larger objects, and light gets bent. So you might think, well, how does I sort of saw people a bit quizzed, and I thought about it too, but okay, so I understand what you're saying. It's the curvature of space-time that we perceive as a force. There is no force, like Newton described, but it's the curvature of space-time. Please explain. I can't get my head around that. And a good way of doing it, we can't see all the dimensions that are going out. Do you want someone to, Daniel, you want to hold this for me? Daniel, do you want to demonstrate it? So this represents, there's two beetles on a flat 2D world, and the common one they use is a pumpkin as the surface which they're on. So I've got my Mars globe, that looks close enough to a pumpkin, and it was I ate the last one last night in the garden. So say my fingers are representing the two beetles. And the two beetles, because of the scale which they're living on, they only see it in two-dimensional. They think they're on a flat surface. You and I stand back on a larger scale, we can see it's curved. They can't. So they quite decide, okay, let's start walking in a straight line parallel to one another. So they keep walking, keep walking, keep walking, keep walking, keep walking, keep walking. And they soon meet up here. How did that happen, they say? And if the clever beetles, they didn't smoke cannabis when they were young. They both doubled. So the clever beetles, they put their heads, they had to think about it. But they suddenly realised, there's some mysterious force. We were walking in a straight line, but we ended up together. There was some mysterious force in the process bringing us together. But us standing back, no, there was no fancy force. It was just a third dimension was going on. Thanks, Daniel. There was just a third dimension going on that they couldn't perceive because they were living their lives on such tiny wee scales. And similar principle, we can't see the curvature of space, but it's there. And that was Einstein's explanation. We experience gravity. We'll talk a little bit more about that later on. Let's have fun with that. So, if I hold my ankle here and I drop it, I still start to think, well, yeah, I dropped the apple, but it starts falling. What made it start falling? And this also is explained. Remember, special theory of relativity showed that space and time cannot be disentangled. They're tied up with one another. And we all know the clock is ticking. In flat space, we've just got linear here. You've got no distortion of space-time. Travelling forward in time causes no acceleration effect on your movement. So if you're still, you stay still. If you're moving, okay, you keep moving. But you don't change in space and just linear space. In curved space-time, so you've got a mass here with this blue. I personally think it's green, but I'm colourblind, so who knows? Ask one of the ladies. Hannah, what colour is that?
Look very ducky.
Okay. Yeah, Marilyn?
Ducky.
Yeah, because you ask the lady what they said colours. They don't get colourblind like us guys. So that represents the mass. Space-time, as we know, these parallel lines start curving inwards and starts heading, converging towards the mass. But also the clock is ticking. You've got time entangled with this as well. So it just starts moving because time is moving forward as well. Time is being distorted. So moving through time also leads to an acceleration and movement downwards. And the reason when I let go of something that falls to the ground is because time is progressing and space-time is being warped. Now, so what properties of the universe does general relativity predict? In other words, how can we validate it? So according to all those formulas, the universe should be getting bigger. There should be black holes out there with event horizons. Gravitational time dilatation, in other words, time should slow down when it approaches masses. Light should get sort of redshifted into higher wavelengths. Light can be deflected, as we showed on that little GIF file early on, can get deflected. We should be able to see gravitational lensing, which we'll have a look at. We should be able to predict gravitational waves. And maybe we've got a better chance of explaining Mercury's sort of interesting orbit. And indeed, all of these have been observed, validating Einstein's work. So let's see what the dog can see. So, yep, there is strong evidence the universe is expanding. These standard candles like type 1a supernovae, quasars, the further look back into time, the further they are, the faster they're moving away from us. There are also patterns within the cosmic microwave background that indicate that the universe is expanding as well. And if you want to go further detail on that, I strongly encourage you to talk to Jonathan. He'll explain all that to you. He's the expert on the cosmic microwave background. Black holes and event horizons. Yep, they've been seen. This is just an artist's impression of Cygnus X1. This was the first black hole that was identified. It's an X-ray binary. So you've got your black hole here, you've got a big blue supergiant, and it's accreting material onto the black disk, which is then getting sucked. As it enters into the black hole, energy gets fires out in these bipolar jets. And that was discovered in the 1960s. It was the first direct evidence observation, yet there's a black hole. We all know these beautiful silhouette picture of M87, supermassive black hole at the centre of M87 galaxy, with a mass of only about 10 to 6 solar masses. So that was April last year. That was sort of another direct evidence for black holes. Gravitational time dilatation. So Einstein says that with the distortion of the fabric of space-time by mass, your clocks should slow down. Yes, they've taken atomic clocks up into the air, brought them down and so on, yet clocks go slower as you increase the gravitational field. So if you want to age a little bit, or you want to age a little bit slower than your buddy, send him up to a high mountain, he's going to age a lot quicker than you are. So clocks tick slower with increasing gravitational field or strength, or with, in other words, increased warping. So if you distort space, you distort time as well. The two cannot be separated, as Einstein said in the special relativity. So with the distortion of space-time, clocks get slower, and that's been well and truly proven with atomic clocks. Also, you get what they call a gravitational redshift. And that's when a photon is trying to escape, say, from Earth or any large mass. It takes energy to get up away from that perceived force or distortion of space-time. They call it a gravity well. So the speed of light remains constant, c. So the only way the photons, if it's got rid of the energy, the photons must become less energetic, which what they call increases the wavelength of them or redshifts them. And that's been shown as well. Known wavelengths of light observed leaving from a large mass, the energy of the photons is reduced, and they're what they call redshift. Here's a quirky question. I threw this. Everyone wants to know, what happens at a black hole event horizon? What's that shoved by maybe out? See ya, bye. Send it out, see what happens. So the bottom line is, he's going to get redder and dimmer. Why? Because as he approaches, the photons leaving that guy, the light's probably something else is going to hit him and get reflected. The photons leaving your buddy as he disappears are going to get more and more redshift the further he gets closer to that black hole, to the event horizon. So which means the light's going to get redder, it's going to get dimmer because the light's shifting away from visual wavelengths into infrared wavelengths. So he's going to get dimmer, red. He's going to start getting stretched out. We call that spaghettification. And that's to do with tidal stretching. The bottom line is that gravity is so strong, his legs are being pulled and stretched towards the black hole at a much faster rate and much proportionally more than, say, his head. So he gets stretched out. They call it spaghettification for good reason. And also his clocks are going to start slowing down. Such that when he hits the event horizon, his clocks will pretty much stop. He'll just sit there and hover on the event horizon. Of course, for the poor old buddy who you sent out, he doesn't know anything about it. He's been ripped apart and killed and long ago. His clocks are just ticking over. He's just getting sucked in. But what you observe, you see your buddy getting dimmer, red, stretched out, and he slows down and then just freezes on the event horizon. Pretty scary, huh? Yeah. So, deflection of light. So, we talked about these geodesic points as the fabric of space-line gets distorted. Here's a picture of the sun getting distorted. We talked about light then travels along these geodesic lines, the shortest path. So light comes along here, but instead of shooting through out here, it gets deflected because of the distortion of space-time. So this is what Einstein's predictions were, and it would here. So if we look here, the light of the star's coming like this, but we look at it and then project it through our own eyes, our line of sight, and we say, the star's over here, but it's really over here. So how do you prove that that's right? And yet it was done after Eddington, the total solar eclipse in 1919. What he did, he knew the eclipse was coming up, he knew exactly where the sun was going to be, what location in the sky at that moment in time. So he ducked out, obviously, prior to that, took some photographic images and made a careful note of the exact positions of the stars, where they were in that particular space of the sky. He waited till the sun then came over, so of course you can't see anything with the glare, but here's the advantage of doing a total solar eclipse. Of course the moon blocks it out, takes care of all that glare, and suddenly you can see those stars. But on this time, in this day, compared with say a few days ago in the middle of the night, the star field's the same, but suddenly you've got that big mass of the sun sitting there distorting that space-time. So it's the same principle. The star's positions should change. The star here that he saw on the night before, without the sun, he would have noted this star would have been here. But in the middle of the solar eclipse, the star appears to be over here. And sure enough, there was exactly the star's position, apparent positions, were altered from the actual positions they knew they should be by exactly the same precise amount that Einstein's equations predicted. They knew the mass of the sun, they used that fancy field equations to work out how much distortion must be going on and the distance to the stars and their positions. Gravitational lensing. That refers to if you have, say, a distant galaxy or whatever way in the distance, its light comes through and then it meets something like a large galaxy or cluster of galaxies between us and that backward source. And the light gets distorted and bent by that. According to Einstein, that should happen. Light gets bent. So it gets magnified, brightened up, and distorted. And they call that gravitational lensing. But, well, how are we going to prove that? Sure enough, you can see the telltale signs of gravitational lensing is when you see these sort of distorted arch-like sort of bits of light here. And what they are is that they're brightened, distorted, magnified images of a galaxy or a quasar way, way back distant in front of this particular galaxy cluster here. And they use their computers and decipher that. You might think, how on earth do they get information out of that? Jeepers, pull the other one, will you? They can. They look at it, they study, they know the process, they just go backwards and they analyse the light and they can tell you what's sitting, billions of light years behind it. Gravitational waves, of course, that was in the press about 5 years ago. Einstein predicted when you get these two big, dense, compact masses spiralling together like that, it's going to cause ripples in the fabric of space-time that are going to ripple out pretty much like water on a pond, like that. These ripples travel out, and they should travel out at the speed of light, and they should be at a certain frequency and pitch to match the objects. And sure enough, with the gravitational detectors that LIGO, that can detect these small little ripples in space-time, and they can tell you exactly what went on. If two neutron stars or two black holes so far away have merged. The precession of Mercury, it matches perfectly. You put Einstein's equations in here, the field equations, suddenly you start seeing the mathematics showing that yes, it perfectly accounts for the precession of the Mercury's orbit and also the shifting of its perihelion. So, but there's a problem with it. General gravity, like Newtonian worked on our sort of familiar sort of scale. General relativity works on much, much larger and to a degree smaller, but a much wider, and it all looks good. But it breaks down when you start getting to, now, you might say, didn't you say that it's field equations tell you what's happening in tiny regions of space? Yeah, infinitesimal, tiny little spaces, but not small enough to account for the science of quantum gravity or the quantum level, which is tiny scales. The mathematics of general relativity breaks down at the really, really microscopic levels, what they call the quantum levels. So at this point, I think I've built up with Galileo, Newton, Einstein. So John Wishart's going to tell us all about quantum gravity. And so John, I'll leave the thing to you. red marker there, slide moving forward there.
I'll just try and attach this to something.
Yep. Or just put it in your pocket, even works quite well.
Yep,
Yeah,
good.
Perfect, John.
Thank you, Chris. I'd just like to acknowledge Chris's contribution to me and my presentation as well. Chris and I go back a long way. He was a student when I was a lecturer. So he's either much younger or I'm much older. I'm not quite sure. This is at medical school a long time ago. Now, the gravity and quantum mechanics. This is a peculiar world, and very hard to imagine it. There's such incredibly small figures involved. You cannot really see or think about them except when they're written down in some way that you can follow. But it is a very weird world indeed. Yet it underlies all that we are. So we're standing here looking fairly solid, and we're standing on a solid floor. Everything looks standard. A chair is a chair. And yet, if you go down, 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 the world becomes very peculiar. And oddly, all of this works. Quantum theory actually works in computers. It works in lasers. And yet, we are also working in the macroscopic world as well. So, where they meet is the problem. So, to try and put a quantum theory in one slide is pretty optimistic. However, there are limits to anything that you like to measure. In other words, there is not an infinite number of values of anything. There are always limits, such as, there's an atomic weight, or there are absorption lines and spectra. And quite a nice thing to think of is say an organ tube, which has sound waves at certain sort of frequencies. There's not infinite number of frequencies. And otherwise you'd have incoherent music. And that is, the H is one of the important thing which we're going to keep coming up against. Next thing, reality is relational. Now that's a very interesting, subtle concept. In other words, whatever you're measuring really only becomes apparent and real by its interaction with something else. In itself, you cannot quite determine what it's up to. It's got to interact. Indeterminacy, this is really strange. In other words, you cannot have a particular set position at any one time. It's a bit like the Heisenberg uncertainty principle. You know the position, well, you know its velocity, but you don't know both of them. But in fact, there is a cloud or a field in which you can predict where things are moving, be they photons, electrons, etc. And they may in fact take up all possible pathways, theoretically. That could be one particle. So we're dealing with profound differences of scale and force. So before with Chris, we were dealing with huge distances. We don't know if they're infinite. They're very big, certainly in scale. The force is tiny. With gravity, you're talking about a measurement is 10 to the minus 11 units, which is just about under a trillionth. So if we just compare and contrast, we'd be dealing with vast distances, weak force, with general relativity. Quantum mechanics has got the following forces: electromagnetic to do with photons, the weak nuclear force, the strong nuclear force. The strong nuclear force is keeping the subatomic particles in the nucleus together. The weak nuclear force is involved in radioactivity, and you have minute distances, which we'll get onto in a minute. Now, you cannot actually subdivide anything down to nothing, if I can put it that way. There is no infinitely small point. There are very, very tiny points, or very tiny lengths and tiny measurements. So the smallest region of space is called Planck length, 10 to the minus 33 centimeters or 10 to the minus 35 meters. Now, it's practically impossible to think of 10 to the minus 33, but it is measurable. It doesn't mean it's gone away to nothing. It is a minute length, but it is finite. Thus, the areas go, as you might expect, if you have meters and then you get to area, volumes, the smallest amount of time, 10 to the minus 43 second, infinitesimally small, but it's measurable again. And Brian Cox says he imagines that's the length of time it takes a photon to go down a Planck length. Smallest mass, electron, 10 to the minus 31 of a kilogram. That's a great deal less than quarks and neutrons and so on. And just thinking about gravitational waves, they are measured in units that are 10 to the minus 21. But they are measurable. They're not nothing. They're not a point without dimensions. There are other sort of limitations in physics which are interesting. Obviously, we know about the speed of light. We know, and we're getting back to H, Planck's constant. And what Planck's constant actually is doing, it's a very small quantum, a small something of anything. This is action, which are controlling a wavelength of electrons and is involved in information. Now, information's got a mathematical connotation. It's not just talking about anything that's a fact. Just to say, that's the measurement of H. Again, minute, but it's there and it's measurable. Information measures alternatives for something, such as in mathematical information says that, for example, a dice that you throw, which has got 6 sides, has information of 6, because there are 6 ways in which the dice may fall. So it measures granularity, and granularity is a big thing in the whole concept of quantum states and quantum gravity. The big thing is that we must think about fields and particles moving in fields. And we know that, for example, a photon is a very small quantity of light. Now, this concept that we've got here, space is a field. And there are fields are living on top of each other. These are minute fields. They in fact are making, according to this theory, we're saying, they live on top of each other. The fields that live on themselves without space-time to support are called covariant quantum fields. Okay. General relativity tends to suggest that everything's smooth, but the quantum gravity approach suggests that space-time is actually granular. And then there are these various trendy terms that creep into the whole idea. There are closed lines in space, which are in looping in form, and they're called threads, and they form what is called a quantum gravitational field. And the lines intersect and have nodes where they intersect. It's sort of a matter of thinking that these minute field fragments are everywhere and together are actually acting as the substratum of space, time, and gravity all intermingled. So that, you see here, we've got nodes and links, and these are called grains of space that the graph represents, and they are all intermingled. This is all on the minute scale. And thus, this gives you an idea of the interwoven elements all forming a teeming network. Now, so the rather strange concept is that there must be some quanta of gravity as well, which can be called a graviton. Now, they're not in space, but they are actually part of space in this theory. So you've got a space-time continuum containing gravity as well. And the space is not empty. There are particles that come into existence and then out of existence. And there's a sort of a stream and a whirling maelstrom of them going on. That's a jokey picture of a T-shirt with all the equations to do with quantum gravity. Now, I couldn't begin to explain exactly what they are, but there's a lot of algebra, and there are things like Sitter spaces and various things like that in it. But every good theory should be summarized on a sweatshirt. Lattice or grid approximation is used to describe strong nuclear forces, which we were already talking about, how the neutrons and protons are making up a nucleus. And that's just a simplified diagram of it. It's not exactly like that, obviously, but that gives you an approximation of what it's like. Now we go on to... Sorry, this looks slightly drunken, but that's my trying to draw on a PowerPoint slide with that pointer. But what that's a Feynman diagram. Feynman, a very famous American physicist who devised, it's a very interesting thing when you sort of look at it. So this could be regarded as looking down on a box, if you like. And in it, it shows you particles that are moving. So we've got electrons going through there. That's one electron. And it's moving through in time. So it's a picture of an evolution of movement and interaction. So then you've got another one going up there and exchanging a photon there and there. Now, just to make it, so really it's a four-dimensional box that you're looking down on, as it were. If you follow, that's a time sequence, and then space is both that way, and that way. So you're getting quite a good lively picture of the movement of a particle both in time and space. Now these later ones show what's so-called weak nuclear force, such that a neutron will eventually can break down, and you will have a positive proton, electrons, neutrinos, and there are these bosons that are part of the particles involved. The thing I like to explain is that, which was actually Wheeler, as already mentioned by Chris, who was a great master of the aphorism, and he could just summarize anything in a witty and meaningful way. And he said that, consider the quantum world. If you were, for example, flying high above the sea, look down, the sea looks smooth and blue and generally featureless. But as you go down, 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 you begin to see the waves, you begin to see the turbulence, you begin to see the movement. And if it's very much similar, if you were, we're standing here as a giant looking at the quantum world, as you go down, 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 you see these maze of particles going in and out of existence in their approximate positions, coming into being by interacting with each other, but always moving in a predetermined, limited number of ways in which they can move, be it orbits or whatever you like, or lines of electromagnetism. There's a limit to everything. And that's a very good way of looking at it, I think. So the solid world is solid, yet there is this tremendous amount of tiny activity going on which gives the illusion of solidity. I mean, well, we are solid, but it's moving at such a pace and such power that we cannot see it, and we can only deduce it. What happens at high energies of quantum gravity is that you get jitters. It's not smooth, and these irregularities, and actually I call them the wild fluctuations, actually give rise to, they were present, of course, after the Big Bang, and that's why things became irregular in the cosmic microwave background. So quantum irregularities are important because otherwise it would be smooth and featureless, nothing would ever settle down into a rocky planet or a star. Now, just to say at this point, quantum gravity is extraordinarily, it's new, it's controversial. There are large numbers of people who don't even believe it. Some people don't think it does any good, but it's an important theory, and it is sort of in competition with the string theory, and you probably know about the string theory with its umpteen dimensions and where every particle is actually a sort of a string, and a one-dimensional string, of which there are at least 10. Very difficult maths. But quantum gravity would be important at the starting point of the Big Bang and within black holes. In other words, when you get to curious places where there's almost infinite gravity, where it is so strong that light can't escape, probably normal laws of physics are breaking down, and both in the Big Bang and black holes, where we're talking about singularities, these are places where it would be possible where you get a proper intersection of big relativity and tiny quantum features. That shows a figurative black hole with loops of the spin network. Roger Penrose, late of the Nobel Prize, just a couple of weeks ago, suggests he said there could be a cosmic censorship, which means that some of the singularities are very hard to get to grips with. However, nevertheless, that's somewhere where there's an interchange, it has to be somehow worked out. It may in fact be impossible to work out, and the string theory may also be impossible to work out. An important man here, Matvei Bronstein, was an absolutely brilliant physicist in the USSR who actually described gravity in the terms of the little particles called gravitons. He was a visionary physicist who made the unfortunate mistake of saying that he preferred Lenin to Stalin, and he was shot. Talked about wiping out the best of brains. Just like Nazi Germany was appalling. Experiments to look into quantum gravity. Now, if any decent theory's got to have some sort of experiment that can be used to prove it. Otherwise, what's the point? You can just speculate indefinitely. If you remember when Peter Feldhofer was talking about time, he said there was a quantum clocks that had uncanny accuracy, and some of the sort of mechanics of that include these remarkable ideas about microdiamonds, central nitrogen atom, would be entangled by their gravitational attraction. Now, if it's a quantum state, which it is, then that's called superposition. And then what you do is and it's all in a strong magnetic field with an ultra-cold vacuum, and you let them fall, and then you measure the spin being a fundamental property of any particle. And according to classical or quantum gravity, you should be able to get differences that show the entanglement is either true in the case of quanta or be showing gravity of the more conventional Newtonian sort. I'm not aware that anybody's actually done this, but this is how it could be done. And the man who's popularized this whole thing greatly, whom you may have heard of or read his book, Carlo Rovelli, his book, which is the sort of popular one, is called Reality is Not What It Seems. He's an incredibly civilized man who's a very arty chap who knows about pre-Socratic philosophers. He's aware of Anaximander. He's written a whole book about Anaximander and Democritus and people like that who had the ideas before the technology. He sees it as a competition, Carlo Rovelli. He says that he does not see any, he can't see that the quantum gravity and string theory are compatible. He says it's a bit like a soccer match, somebody's got to win it, or perhaps the Bledisloe Cup. So currently we can't combine the general theory of relativity with quantum field, we need an experiment to some degree to try and get some sort of connection between the two. Carlo Rovelli was an interesting chap. When he was a student, you know how students have up on the walls of their rooms, they tend to have posters. He had a nice poster up with 10 to the minus 33 on it, so he was thinking of Planck length even at that stage. And we're getting on to some slightly more unusual things to do with gravity here. But David Tong, professor of theoretical physics, considers it may be possible to reconcile string theory and quantum mechanics and classical gravity. So that's one approach. What I was greatly taken by was the website from the Max Planck Institute for Gravitational Physics, or brackets, Albert Einstein. The Max Planck Institute has a deeply impressive website full of deeply impressive people who are tremendously bright at doing fundamental experimentation, and they lecture internationally, and you can actually go there and join up with courses and be in touch with first-rate minds. And they're looking at such things as, hang on, let's go back a bit. They're looking at, let's go back again actually, things like the geometry of discrete structures, the Planck scale. String theory may require modification of general relativity, the Planck scale. And we may get underlying string theory may resolve quantum field theory and general relativity. And they look at all of those things they are discussing and looking into as deeply as possible. So that was they're very impressive looking. Max Planck Institute looks actually into all sorts of questions, not even just this. They are a deeply impressive group. Even getting slightly more avant-garde, we've got Professor Claudia de Rome. And she's a rather amazing individual who's actually been in the European Space Program. She's a qualified pilot and also is professor of physics. And she has got this quaint, perhaps, idea called massive gravity. First presented 2011. It suggests that gravitons are not massless. And if so, gravity should have a weaker influence over large distance scales, such that where the universe expansion is accelerating, it may actually slow it down, so it's not going to go accelerating forever. She's won a lot of prizes and obviously is well regarded. The expansion is certainly thought to be produced by dark energy, and gravitational wave astronomy may help this to some degree. And some of these really strange ideas. Speed of gravity. Does gravity move at different speeds through materials? Are there gravitational rainbows? Something to think about. Dr. James Farnes, Oxford, has proposed a new model which unifies both dark matter and energy into a fluid, which he says can possesses a negative mass, and it can be called negative gravity. Now that is their repulsive gravity. Now gravity is supposed to be attractive. In fact, or as Chris has explained, actually you're moving in a straight line through space-time. But Brian Greene says it's a bit like pushing on a sort of a bag that formerly contained crisps, perhaps, and it sort of pushes back at you. And he uses that as an analogy for so-called repulsive gravity. And Chris again might be interested in, it may provide an explanation of these halos which are around galaxies, or maybe part of the business of why galaxies are rapidly rotating and they still cohere. Now, I hope that hasn't completely confused you. My wife said, don't go talking on and making everybody go to sleep. So looking around, I think most people are probably still awake. So.
John, that's very good, thank you. It's quite fascinating, isn't it? Thoughts, people are working all around the world. You think, guys, all these different thoughts and stuff. Is it a modification of general relativity? Is it something totally new with quantum? I know sort of Sean Carroll, a popular astrophysicist, sort of theoretical physicist who came out to New Zealand recently. His belief is quantum physics at the end of the day is just appears to be faultless. It's one of the most successful, probably the most successful theory that's ever been brought about us by humans, and his belief is we've got to start nuts and bolts with quantum physics and build up from there a new theory versus trying to patch up the current theories. So here, let's talk about just a brief wrap-up summary. I can't resist myself in putting quirky slides and cats in there. And I think this, if someone says the world is flat, or you say, well, how come there's an ongoing supply of pens? Cats would have pushed them all off by then. And cats don't play, they just stay in gravity, okay? That's what he does. So, we know it's a fundamental attractive force. It is over the long range force. As John was saying, out of the four fundamental forces, it's the weakest one by far. From strong nuclear, weak nuclear, electromagnetic and gravity. Newton's law, universal law, that was clever at its time, but clearly that was not complete. Einstein was absolutely brilliant and patched up a lot of holes and showed us some stuff. It's been verified numerous times, but it is still, it's successful on large scales, but clearly it's incomplete as well. Quantum gravity on the really tiny microscopic scales, and that really, as John was alluding to, it is the subject of all the future studies. That's where it's heading, and it's all going to be part of the holy grail, i.e. the theory of everything. Whoever brings that together, if any of you guys come up with the answer, don't tell anyone, come straight to me. It's like when patients say, why is my blood pressure, what causes it, doc? I go, if you ever find out, don't tell anyone, come straight to me. There'll be a Nobel Prize in it. I think that's what it is. Okay, so your homework, you've got two things. One is, get one of your friends and explain what the equivalence principle is. In particular, so it's independent of mass. There's a YouTube video of David Scott, who Marilyn knew very well, Apollo 15 experiment. This is a painting from Albin, one of the moon landing astronauts. He was the lunar module pilot on Apollo 12. He did some artwork of the lunar landings, and he did that painting there of David Scott doing it. There is a video, there's numerous versions of the YouTube, but it's a really good video. I've actually screened it here and stopping it going together. Now the other part, here's some food for thought. Discuss this with potential ex-friends, if you like, so engage them in this conversation. So we know from special relativity that movement makes clocks slow down, so if someone's going a lot quicker than you, they appear to slow down. We know from general relativity that mass does the same, your clock slows down. So is it a feature of gravity that all objects move to regions where time runs slower? That's what's attracting the apple. I told that to a friend recently. She said, so what you're trying to say there is the apple just wants to live a little bit longer. I said, well, would you if you were an apple? Rather than be big. So maybe, does that think that objects are just moving to regions with time, so they're starting to get in motion, because motion slows the clock down. They're heading towards mass, that slows the clock down. Interesting thought. Is it the slowing of clocks, the closer we get to, say, sea level, that increases the gravitational pull we feel? Is that what's holding us to the floor? Is because our clocks are slowing down? That, you remember I said warp space-time gives us the precision. We think it's warp space-time. Is it just the fact that the clocks are slowing down? Is that what's holding us down to the Earth? Yeah. Does the apple fall because it seeks a place where times run slower? Everything naturally has an innate desire to live for longer. Does gravity dictate the flow of time, or does time itself define gravity? So, food for thoughts. Next dinner party, guys. Watch out for the food fights. Food for thought. So, I hope, so that's pretty much it. Gravity, past and new ideas. I hope you've enjoyed it. Thank you very much. For myself or John? We've covered a bit tonight, so...
Thanks very much.
Yes?
It's not really a question, but I was intrigued. I listened to Brian Greene make a comment that if there is such a thing as a string, and you expand it up to the size of a human being, then the nucleus of your atom would be about the size of a galaxy. So is that getting a sort of a conceptual 10 to the power of 33?
I think it does, yes, it's stunningly small, but it's not, it doesn't go to nothing.
No.
The things are not infinite in small scale. They could be infinite in a big scale, we don't know, but it's quite comforting to think that there actually must be a limit somewhere. You're not going to go into absolutely nothing.
And you can tell him I was a good student, wasn't I, John?
Oh, yeah. Yeah.
That's good. So I put this up here. There's some really cool stuff. I put together some extra bonus slides, just further explanation. I went into further depth with Einstein's field equations and some further ideas on gravity and stuff. There's a really good YouTube stuff in that you discover. So if anyone's interested in delving a little bit deeper and you want some sort of bonus slides, just flick us an email and quite happy to provide you with that.
One other humanistic thought. The reason that Eddington was so keen for Einstein to be recognised and for to be proved, Eddington was actually a Quaker, he was a pacifist, and he was so distressed by the mayhem of World War I that he felt it was absolutely desirable for German science and British or any other science to be combined and understood together, and that was a very good idea.
All right, guys, thank you, John. Everyone drive home safely, but most of all, have fun. Good night. Good, John.